Hello, welcome. Today's video is about trigonometric substitution for integration, and our objectives are basically to learn how to do this to find integrals. You can look up on your own the real life examples in your textbook. I'm going to skip that in today's video. So basically, if we have integrals involving any of the expressions of a square root of a squared minus plus or minus u squared, or vice versa, u squared minus a squared, those are the things we're going to use this method for. So that's what you're looking for in your integral. And then we have these Pythagorean identities, which also might be helpful. So if we have cosine squared, that's 1 minus sine squared. Secant squared is 1 plus tangent squared. And tangent squared is secant squared minus 1. So how might these Pythagorean identities and trig expressions go together, or these radical expressions go together? So how it might be helpful is if I have something like a squared minus u squared, I can rewrite that so as a squared minus a sine theta squared. So basically what I did is I let u equal a sine theta, and so I know that no matter what u is, okay, so u is some function of x, that now my new variable is theta, that for any a, so a is a number like 3, 4, whatever, that I can find a theta such that sine of that theta is going to be equal to whatever x value I need. Okay, so I still have two variables. I still have x in my expression of u, and then I have the variable theta, so they are kind of a little bit dependent on each other. So it's kind of like u substitution, but a little bit different. Okay, so if I let that happen, now my radical is a squared minus a squared sine squared theta. Factor out that a squared, so then I get that 1 minus sine squared theta, which now I'm going to use that Pythagorean identity, and I have a squared times cosine squared theta. And so then I get a cosine theta and get rid of the radical altogether. So this is kind of the process we're going to be following in all of our problems. Here is a table that can help you with your trig substitution. So if we have something of the form the square root of a squared minus u squared, then your trig substitution is letting u equal a sine theta like I did above. If we have a squared plus u squared, then we're going to let u equal a tangent of theta. And if we have the square root of u squared minus a squared, then u is going to equal a secant of theta. All of the domains that they talk about here, you do not need to know these. These are just to make sure that your functions are one-to-one and have inverses so that they work. Don't worry about it. It's not going to be a problem. And then the other thing is there's these triangles, which I'm going to show you how to draw on your own because you're going to need to refer to them later, but you don't have to memorize them. They're pretty easy to come up with on your own. So they are helpful. So you have this table to refer to everything. So we're just going to go over 4 examples today. So the first one is find the integral of 1 over x squared times the square root of 9 minus x squared dx. So the first thing I notice is I have 9 minus x squared. So that's my a is going to be 9, or a is 3, and u is x. So then I'm going to let x equal a sine theta. Okay, so that means I have x is going to equal, u equals a sine theta. And so then I have x equals 3 sine theta is going to be my substitution. And it's going to be really helpful to go ahead and take the derivative of that right away. So then I have 3 cosine theta d theta, because when we do our substitution, we also want to substitute that dx. Okay, so now if I go back to my integral over here, I'm going to have 1 over, and then I am going to go ahead and replace my x squared. So I have 3 sine theta squared. And then my radical is going to be 9 minus 9 sine squared theta, once I square that again. And then my dx on the numerator is this. So my numerator is 3 cosine theta d theta. Okay, so lots going on here. So my dx replaces there. And then my x squared and x squared, I substituted that in. So now everything is in terms of theta. So once I do that, then I can go ahead and simplify. Oops, let me change that. 9 cosine, oops, not cosine, sine. My goodness. 9 sine squared theta. And then I can pull out a 9 here, 1 minus sine squared theta. So then I have 3 cosine theta on the numerator. And then I have a 9 sine squared theta. And then in the radical, I have a 9 cosine squared theta. And so when I take the square root of that, that's 3 cosine theta. So this will cancel with this. And then I'm going to pull out the 1/9. So I have 1/9. Oh, sorry, I didn't mean to switch colors there, but I did. So essentially I have 1/9 times the integral of cosecant squared theta d theta once I simplify everything. And then the antiderivative of secant squared is cotangent. So I have negative 1/9 cotangent, and you should find that on that formula sheet, plus c. But now I need to go back to my original variable. So the original variable was x, not theta. So I need to put this all back in terms of x. So this is where that triangle is helpful. So if we remember, x equals 3 sine theta. Okay, so we had x equals 3 sine theta, which means that sine theta equals x over 3. So then I can make a triangle where I have theta, and then I have opposite is x, hypotenuse is 3, and then I can use Pythagorean theorem to figure out that this side is 9 minus x squared, but that should also match that radical expression that we had. But it's really good to use Pythagorean theorem to make sure you did the correct substitution in the first place. Okay, so now because of that, I can look and say, okay, what is cotangent of theta on this triangle? So then I can find that cotangent of theta is going to be 9 minus x squared over x. Okay, so I'm using the triangle to figure that out. So now I have negative 1/9 times the radical of 9 minus x squared over x plus c. All right, so hopefully now that you've seen the first one, it's a little bit quicker as we go through other ones. So the next one is where we have tangent involved. So this one we have 4x squared plus 1 under the radical on the denominator. How exciting. So if I look at this, my u value is going to be 2x and my a value is going to be 1. So I'm going to let 2x equal tangent of theta. So then I get x equals 1/2 tangent of theta. And then dx is going to be 1/2 secant squared theta d theta. So then I'm going to go through and do all of my substitutions. So dx on the numerator is 1/2 secant squared theta d theta. And then on the denominator here, I'm going to get that, well, 2x equals tangent theta, so 4x squared is going to be tangent squared theta, and then plus 1, which is nice because now I don't have to do any factoring. I can just go ahead. I'm going to take that 1/2 out front, actually. So now I have secant squared on the numerator, and then I have square root of secant squared on the denominator. So then I just have 1/2 times the integral of secant theta d theta, which then if I use my handy dandy formula sheet, it's this long thing with natural logs and the absolute value of secant theta plus tangent of theta plus c. Now here's the trick. We got to go back to our original variable, which is x. So if I make my little triangle over here, I'm going to do that in a different color. I started with tangent of theta, oops, no, let's go back. Tangent of theta is 2x. So on my triangle, I want opposite over adjacent to be 2x, so 2x and 1, which means then using Pythagorean theorem, I can get that this is 4x plus 1, which matches my radical expression in the beginning, so that's fantastic. So then if I look at this, my secant is going to be square root of 4x squared plus 1 over 1. So, and then tangent we already have. Tangent is going to be 2x. So then I have all I need to go ahead and substitute those back in. So then I have the natural log of the absolute value of 4x squared plus 1 plus 2x plus c. All right, let's try another one. We got 2 more to do. So our next example is now we have a rational power on our denominator. So what I'm going to do here is I'm just going to rewrite this as 1 over x squared plus 1 cubed underneath a radical. And then I can say that, oh, okay, from here, a is going to equal 1 and my u is going to equal x. So I'm going to let x equal tangent of theta. Okay, based on that table, that's how I figured that out. Because I have, let me put the cube on the outside of the radical. So all of this gets cubed. Okay. And so then I'm going to take the derivative. So the derivative of tangent is secant squared. So now I can go ahead and do all of my lovely substitutions. So dx is going to be that secant squared d theta. And then under my radical here, I have x squared, so tangent squared, plus 1. And then all of that gets cubed. And so then I'm going to end up with secant squared d theta on the top. And then I have the square root of secant squared, so secant cubed on the bottom. Guess I can put the d theta on the side. It looks a little better. Okay, so then I have 1 over secant, which is cosine. So I'm really, oops, not cosine squared, just cosine. So I'm really just integrating cosine, which is sine, plus c. Now I got to do the little triangle trick. So if I started with tangent being x, so here's my theta, tangent being x, then my hypotenuse is going to be x squared plus 1, which matches my radical in the original problem, so that's fantastic. So then the sine of that would be x over x squared plus 1. Square root of x squared plus 1 plus c. Fantastic. All right, our next one and last example has bounds. So we have a definite integral here. And so what we're going to do on this one is first we're going to figure out which scenario we're in. So I have u squared minus a squared. So my u is x and my a value is square root of 3 in this case. So we got an extra little radical there. So looking at my scenario here, this is going to be a secant substitution. So square root of 3 times secant of theta is what we're going to have x equal. Take the derivative of that right away. So then I have square root of 3, square root of secant, or sorry, derivative of secant is secant tangent d theta. Fantastic. Okay, so now when I go through and do this, my substitution, square root of 3, oops, I want to make sure that since I'm changing variables, I make sure I remind myself this is still x equals square root of 3, and x equals 2 until I change those. And in my numerator here, I'm going to have 3 secant squared theta minus 3. And then my denominator is square root of 3 secant theta. And then dx, oh, I need to substitute in my dx. Okay, and then dx, we have square root of 3 secant theta tangent theta d theta. Oh my gosh, got lots going on here. All right, so what can cancel? I think this whole thing can cancel with that whole thing. And then my numerator here, I'm going to factor out a 3, so then I get secant squared theta minus 1 times tangent of theta. And then, yeah, that's it. D theta, my whole denominator canceled. And we can change our bounds now too. So our bounds are in terms of x. Let's change them to be in terms of theta. So if x equals square root of 3, so let's see here. If x equals 2, then I have 2 equals square root of 3 secant theta. So then I get 2 root 3 equals secant of theta. I'm not very good with secant, so I'm going to change this to cosine. So then that means square root of 3 over 2 equals cosine theta, which implies that theta equals pi over 6. So where 2 was, I can now put pi over 6. And then if x equals square root of 3, that implies square root of 3 equals square root of 3 secant theta, or cosine theta equals 1, because secant and cosine are both 1 at that point. So then theta would equal 0 in that case. So then I have 0 to pi over 6 are my new bounds in terms of theta. And I'm going to go ahead and simplify that radical. So 0 to pi over 6. We have the square root of 3, and then secant squared minus 1 is tangent squared. So then I get tangent of theta times another tangent of theta now gives me tangent squared theta. I hope I didn't move too fast there. But if you remember, when we have powers of tangent squared, it's actually easier to make those secant squareds. So I'm going to pull out my square root of 3. And I'm actually going to write this as secant squared theta minus 1 instead of tangent of theta, because the antiderivative of secant squared is tangent. So now I have square root of 3, and then I have tangent of theta minus theta when I go ahead and take the antiderivatives. And then I want to evaluate at my bounds. So I'm going to go ahead and plug in 0. I get 0, 0, 0. Plug in pi over 6. I'm going to get the square root of 3 times tangent of pi over 6, which is 1 over square root of 3. And then pi over 6. And then I'm minus 0, minus 0. So my final answer would be 1 minus square root of 3 pi over 6, which is approximately 0.0931. Okay, so lots going on here. I know these are super tricky, so give the examples I showed you or give the homework problems a try.